Okay, our next speaker is Tim Stubbs from Goddard. He is part of the DREAM team, which is the NASA Lunar Science Institute team led by Bill Farrell. And he's going to be speaking to us about lunar surface charging and dust transport during the passage of a coronal mass ejection. Take it away, Tim. And Tim, are you able to turn on your camera? There we go. Almost. Great. We see you.
All right, great. Okay, so I'm going to talk about lunar surface charging and dust transport during the passage of coronal mass ejection. And this is sort of some modeling predictions based on real solar wind data. So, our motivation is to understand the response of the lunar environment to highly variable and extreme plasma conditions encountered during the passage of a coronal mass ejection. And so this is a component of the solar storm lunar atmosphere model, SLAM, that was part of a DREAM team effort. So the way we're going to approach this is to use a lunar surface charging model to investigate surface potentials and electric fields during the May 1998 space weather event. And this is one that's been studied quite a bit by heliophysics people. And but because we're looking at the moon, we're interested in maybe assessing the effects on charged dust transport and other things. And so one of the things we're interested in is determining the influence of various current sources to figure out which processes are important and which ones aren't. And also we want to investigate which parameters observed upstream of the moon could be used as indicators of impending extreme conditions on the lunar surface. So first I'm going to give a quick overview of the lunar plasma environment. So here's a popular sketch here of the plasma environment around the moon and surface charging. So, okay, so the lunar surface is electrically charged by solar ultraviolet, plasma electrons and ions, and secondary emission. And that secondary emission of electrons from incoming particles. So an incoming particle comes in, knocks out electrons from the surface. And so one important thing to appreciate about surface charging is that it's an electron-dominated process. Pretty much everything about the E field and the surface potential, it's all based on the properties of the electron populations. Okay, so so some basic characteristics. So on the day side in sunlight, the lunar surface is positively charged by the photoemission of electrons by solar UV. So then on the night side and near the terminator in shadow, the surface tends to charge negative due mostly to the collection of plasma electrons. And although I won't go into too much detail on the lunar wake, so downstream of the moon there is a sort of a plasma void region that forms, which is sort of very, very tenuous. And but you can see on the diagram there, I've marked the subsolar point and the terminator regions, which are the ones I'm going to focus on with this study. And so the subsolar point is basically the equator at midday, and the terminator is sunset and sunrise. Okay, and just quickly mention that surface charging, the plasma sheath, and dust is all part of the lunar environment, and these components can couple to other aspects of the lunar environment, like the ionosphere and the exosphere. And so, if you look at the lunar environment so holistically, these things all kind of couple to some extent or another. And so, just to put these processes in context. Okay, so get into what I actually did. So the lunar surface charging modeling. So I took a model that I worked on with various colleagues. So I started with that approach, so to investigate the surface charging at the subsolar and terminator regions. And so basically this model has about 11 basic assumptions, including the moon can be treated like a planar surface because it's so big compared to the scale length in the plasma, and various other assumptions. And so then we basically take analytical expressions for the currents incident at the moon and then solve numerically to find the equilibrium surface potential. So that's quite a common approach. Okay, so for the solar UV, so for the photoemission current, we've assumed sort of a moderate sort of mid-cycle photoemission properties, And so we picked sort of 10 microamps per meter squared in a photoelectron temperature of about 2 eV. And these are sort of based on numbers sort of based on the work by Stubbs et al. Okay, so for the plasma conditions, we had the plasma electron and proton moments from wind and storms, and these were derived assuming a Maxwellian distribution. And for the energetic particles, so for the energetic electrons and protons, we had data from wind, ACE, and SOHO. And so these were combined as an integrated flux of particles for particles above 10 eV. And this process was described in a paper by Halakis et al. Okay, so that's basically a fixed current. So we assume, assumed in that is that the lunar surface doesn't charge above 10 kilovolts negative. And when we started out, that was a reasonable assumption because I think LP, the biggest potential it had seen was about 4.5 kilovolts negative. Okay, so continuing. So when we include secondary emission due to plasma electrons, we again assume Maxwellian velocity distributions. We use the Stern-Glass relation, the expression, and we use that and characterize that yield by some measurements from LP from Halakis et al. So we assume that secondaries from plasma ions were negligible, so which is pretty reasonable, and then, but for the secondary, emission properties of the lunar regolith for the more energetic particles, we took aluminum as being a proxy, and we estimated yields of about 0.1 for energetic electrons and 5 for energetic ions. Okay, so when we did our runs, we did more than one run because we wanted to sort of investigate the influence of different current sources. So we started off with case 1, where we just included photoemission and the plasma electron and proton currents. So then we took case 2, which is the same as case 1, except for we added secondaries from the plasma electrons. Then we had case 3, where it was the same as case 2, but we then added the energetic electron and ion currents for particles above 10 keV. And then for case 4, we then added some secondaries for those energetic particles. So these are the upstream solar wind conditions that we use for this modeling. And so the top panel shows the interplanetary magnetic field. The next panel shows the plasma concentration. Then next to that, you've got the ion and electron temperatures. And then below that, you've got the fluxes of the energetic particles. And then at the bottom, you've got the solar wind flow velocity. Okay. And I might just add that you can see that it's probably just about make out there's a dotted line on some of the panels, and that's sort of nominal conditions. So you can see that basically all of those parameters kind of vary by about an order of magnitude or so about sort of nominal conditions. And so during the CME, the conditions can get quite extreme in both directions. So we've marked some vertical lines there. So these are the CME interval that Farrell et al. Focused on. So the first line marks out some nominal solar wind conditions. Then the second line kind of marks out a shock, so that's when you get sort of dense and fast and hot plasma. And then we've got the early CME after that, which is cool, tenuous, and very fast. And then finally the late CME, which is very dense, very cool, and fast. And so we'll kind of like pick out some of the effects that would have on our predictions for the lunar environment. Okay, so first up we've got surface charging predictions at the subsolar point. And so here on the top panel we've got our predictions for the equilibrium surface potential. Then below that we've got the predictions for the Debye length, which is basically the scale length in the plasma. And then next we've got the surface electric field prediction. Then in the second to last panel we've got the predictions for the secondary electron yield. And then the bottom panel we've got the predictions for the solar zenith angle for the dead zone. And that's basically defined as the region on the day side where you transition from being positively charged to negatively charged. Okay. So, so in cases 1 and 2, so they were both sort of dominated by photoemission. So basically the surface charged positive as you'd expect. It never goes negative. And also secondary emission does seem to have a little bit of an effect. So there was some significant variation during the CME passage. So the variation in these parameters of maybe a factor of 2 or 3. There's quite a lot of change. So you probably might notice that cases 2 and 3, that's the green and the purple lines, are hidden by case 4, and that basically is telling us that the energetic particles can be pretty much ignored on the day side, so they don't really have much of an effect.
And you have 3 minutes.
Okay, so the secondaries can have a big effect on modification of the dead zone. That's something quite important. So although the surface potential is quite variations, difference is small, it can have a big effect on the dead zone. Okay, so then we look at charging predictions at the terminator. So same panels as before, except for at the bottom now we're showing the currents. And so there's a hierarchy of currents. So the current from the plasma electrons tends to be biggest, then it's followed, the next most important is the one from the plasma ions, and then it's the currents from the energetic particles. And so again, so around in this region, we're dominated by the plasma electrons and secondaries, and we're always negative. Highly variable this time, instead of being factors of 2 or 3, we've got order of magnitude variation. And then, so at some points, the energetic particles can be important for brief intervals, and I've marked out a little grey circle here on the right-hand side, and the next slide here zooms in on that particular event. And so I'm showing potential, secondary yield, currents, and then the current ratios at the bottom there. And so basically what we found was when the energetic electron current is comparable with the plasma ion current, then that basically means that we're seeing very briefly potentials in excess of 10 kilovolts negative. That's what we think we're seeing. And so when you look at those current ratios at the bottom, whenever we spike there above 1, that means we're getting very, very big short-lived potentials. And so if you've got very good eyesight, you can see that whenever we get those spikes above 1, we have a dropout in our predictions for cases 3 and 4. And given our previous assumptions, that basically means the model can't find an equilibrium because it's not possible for the ions to sort of find an equilibrium with the incoming electrons. So one suggestion is that we could in future sort of monitor the energetic electron current and ratio with the plasma ion current, and that could maybe give us a warning for extreme events at the moon. Okay, so then briefly, so we consider some predictions for spherical dust grain with a radius of 0.1 microns. So we consider these parameters. So the minimum dust grain potential required for electrostatic forces to exceed gravity just above the surface. Then we consider the electrostatic levitation equilibrium height for a dust grain with a nominal potential of 1 volt. And then we consider the lofting maximum achievable electrostatic lofting height per volt on the dust grain. And so these predictions don't make any assumptions about how the dust grains are charged or ejected, but just rather illustrate the effects of the CME on the dust in the exosphere. So okay, so here are some predictions. I probably ought to hurry up. So as before, on the day side, you're seeing sort of variations of a factor of 2 or 3, and around the terminator, variations of 1 order of magnitude. So in the sort of heights you can get to on the day side and near the terminator. So the main message from these 2 plots is that so dust charging and transport tends to be subdued near the subsolar point and enhanced at the terminator regions when the plasmatic conditions become more extreme. And by that I mean sort of denser and hotter. And this is primarily due to the increase in the plasma electron currents, which tends to sort of subdue the potential on the day side and sort of enhance it around the terminator and on the night side. And, okay, so I can get into my summary and conclusions. So even during CMEs, the surface charging in the subsolar regions and terminator regions is typically dominated by currents from plasma electrons, secondary electrons, and plasma ions. However, in the terminator region, if the energetic electron current is comparable with the thermal plasma ion current, so this ratio here is about 1, then it's possible that that's an indicator that you're going to get some extreme sort of kilovolt charging in a negative, and that's maybe something to look out for. So, and of course, we've just considered the terminator region here, so we'd expect this to be more extreme in the wake, where the plasma currents are further reduced relative to those from the energetic particles, and so this could be an even better indicator in the wake. as I suggested, we might want to in future sort of monitor the ratio of the current of the energetic electrons to that of the plasma ions upstream, and that might warn us of some sort of impending transient extreme event at the moon. And I might just add that those events, when you've got very sort of spikes in the potential, were only in the order of sort of hours. They're very kind of short-lived. And then just a recap on the dust charging and transport. So that's subdued at the subsolar point and enhanced at the terminator regions as seeing conditions get more extreme, sort of denser and hotter. Okay, that's it.
Great, thank you so much. Okay, well, we kind of used up all your time for questions, and there actually are no questions yet in the chat box. So what I suggest is, as people think of questions for Tim, you just go off into the chat box area and talk together at that point.